Hey, what's going on everyone? Today we're going to learn about how to solve another linear programming problem by using LpMinimize. So let's read the problem here. A wedding planner must determine guest seating allocations for a wedding. The wedding planner wishes to maximize the total happiness of all the tables. Tables with higher differences between the first and last guests' alphabetical order are considered happier. The max number of tables is 5, and the max table size is 4. So if we want to use the library package PuLP, let's first go ahead and import it. As you can see, I only typed import PuLP. From other problems, we had written this. But we're not going to use that in this problem, just to demonstrate how using this function will just make it easier for us to write code. Because if we don't write that, we have to preface everything with PuLP. So it would be PuLP dot whatever function you want to use. Now from the problem, let's add the variable and the values of max table size, and guess. So the split method, if you're not familiar with it, in Python, it breaks a string into a list using white space by default as the delimiter. Each sequence of characters between spaces becomes an individual element in the resulting list. So let's look at how, if we print the results of guess, let's see what it looks like. So here we have a list separated by using the delimiter of the space, so it's going to be A all the way to R, and it's going to be a list. Now let's define the happiness function that calculates a happiness score for a given table by finding the maximum alphabetical distance between the first and last guest names at the table. So we're going to create a function called happiness. It's going to receive one parameter as the table, and we'll see how that works later in this problem. So this is going to be the function, and I'll explain this right here. ORD table 0. So it's using the index of 0. It's grabbing this, and what that's going to be, it's going to be a character. So just to demonstrate, so ORD character converts a character like, and I'll use A as an example, A and C. So if I run that, I'm going to get a Unicode character, or a code point of 65 and 67. So what this is doing is it's subtracting this value by this value. The Unicode values are the first and last guess at the table. So -1 is going to capture the last element found in the list. or in the table. And the table is going to be a tuple, which we'll define later on. ABS ensures the result is positive, which, it's an absolute value. The happiness function is used to evaluate the desirability of seating arrangements in the wedding seating model. So tables with higher differences between the first and last guest alphabetical order are considered happier, as stated earlier. So let's now create a list of all possible table seatings. So we'll create a new variable. So notice how I have to put PuLP before writing any method, because I didn't do from import PuLP import star, or from PuLP import star. So we'll just print it just to see what we get. So this code generates all possible combinations of guests for tables, with the maximum size determined by max table size, which we established before is 4 guests. And tuple C converts each subset into a tuple, and tuples just ensure immutability and compatibility for further processing. And then all combinations, this method, is used to generate all possible subsets of a list up to a specified maximum size, which we determined right here. So if we look at this output, we see it goes A, B, C, and then it'll go A, B, A, C, A, D, and so on and so forth, until we get combinations that include 4 values in the tuple. Now, next, let's initialize the linear programming model, and the goal is to minimize an objective function. So we'll call it seating model. And we'll go ahead and print it out. And it's going to show us nothing yet because we haven't defined any objective function or constraints or variables. Next, we need to create a dictionary of binary decision variables where each variable corresponds to whether a specific table combination of guests is selected, which we'll establish as 1, or not selected, which is 0. So we'll define it as x, the decision variables. And we'll go ahead and print that and see what it looks like. So lpVariable.dix is a function from the PuLP library to create multiple decision variables efficiently. And the variables are stored in a dictionary with keys from possible tables. And we put table here is the prefix for naming the variables, which will appear as table and whatever the combination is. So here it's A, table A. So, and then low bound is equal to 0, up bound is equal to 1. So 0 meaning the table is not selected, 1 meaning it is selected. So therefore, since the range is 0 and 1, 0 to 1, these variables are going to be binary. Now we need to add an objective function to the optimization problem. So we just use the plus equals to the linear programming model of seeding model. And we'll just go ahead and print that out again. So here we have the model, and this is the objective function. So this whole thing. These are going to be the variables. Just to show you variables right here. So the goal is to maximize happiness by assigning guests to tables in a way that maximizes the total happiness score. So just you can see right here, there's going to be a number next to each table, and so that's going to be the happiness score. So we could see 7, 8, 9. We see these values in front of the variables. There's 16 right here. And X table is a decision variable, indicating whether the specific table is used or not. And then PuLP sum aggregates the weighted happiness values for all possible table configurations. The summation ensures that only configurations with X table equals 1 or active tables are contributed to the total happiness. Okay, after establishing the objective function, let's add a constraint to the seeding model, ensuring that the total number of tables used does not exceed a specified maximum. So the specified maximum is the maximum number of tables, which we established as above being 5. 5 is the max tables. And then we'll print it again and run that. And what's different about this, it's going to show us the constraint. It's a very long objective function right here, but we need to scroll down until it says subject to. So it's subject to this equation. So this right here, it calculates the total number of tables used by summing the decision variables. Each of the X table can only be 0 not used or 1 used. Since it's defined as a binary variable, the value of our max tables variable that we established earlier is 5. So it cannot be greater than 5. The next set of constraints that we must create will define the set partitioning problem by guaranteeing that a guest is allocated to exactly one table. So a guest can't show up in multiple tables. So for a given guest, so we're going to run a for loop in the guest list. We're going to add all these constraint equations. So for a given guest, this sums up all the binary decision variables for tables where the guest is included. If a guest is assigned to a table, X table will be 1, otherwise it's 0. Now we can solve the problem as well as show the solution. So we solve it right here, seeding model.solve, and we print out the total number of tables. So here, an optimal solution is found. And out of 4,047 possible combinations, these are going to be the tables that satisfy all the constraints and conditions in the problem. So it's going to be a table MN and then 4 other tables with 4 guests at each. So that's a wrap for this video. Hope you learned something, and thanks for watching.